Mark is going to lead us off with his proposal on SES that was made to TC39 recently, which would be an excellent starting point. Patrick has materials prepared on his work that implements most, not all, I don't remember anymore, most of this. I've got some notes both on some open topics around SES and TC53, and then kind of SES and networking experiments, adventures to see how that might go. So it's going to take some time. This is dense material, so as Mark was saying earlier, questions in real time are very encouraged, so we don't get too far with things being clear. And then if people didn't hear, Mark is going to record his presentation to be able to post that publicly later. And we'll end the recording when the presentation is finished and we're into discussion.
Okay, great. So today I want to explain the progress we've been making on SES, and in particular, the Compartments API, which was started by Patrick and refined a great deal by J.F. Paradis of Agoric. And in the process, give you a from the top orientation in SES and what it's about. So I'm trying to make this presentation somewhat self-contained, not with the first half, not assuming any deep expertise on JavaScript. So please interrupt me for clarifications if something goes by that was puzzling. Okay. So there are several different constituencies for SES that use SES for very different patterns, and very different patterns for very different use cases. And one of the things that's been very satisfying is the fact that SES is useful across this great diversity. Agoric is using SES for smart contracts, and when we run it on the blockchain, we're using the XS machine. When we run it on solo machines, we're using Node, but we're writing all of our code in SES and making use of the security properties. Node itself has been adopting elements of SES and providing more direct support for SES in Node, and it'll and they'll be using it to address the problem of least authority linkage, which I'll be explaining in a moment. On the browser, there's Salesforce. The current SES was constructed in a collaboration between Agoric and Salesforce. And Salesforce is using SES at quite a lot of scale. And there's MetaMask, which is a browser extension and framework for doing wallets and client sides of dApps, for dApps being applications written for a decentralized blockchain. And MetaMask, there's tremendous amounts of money at stake on the integrity of the operation of the MetaMask user interface. And then, of course, there's XS, the JavaScript machine constructed by Moddable for purposes of embedded. And there's TC53, this organization. And it's the view from TC53 that was really the clarifying one with regard to the evolution of the compartment API and how to solve the problems that it solves in SES. Because the others have a set of trade-offs that are more similar to each other. Embedded has a set of trade-offs that are more different. And the direction that the embedded use case faced us with really clarified some things that actually helped all of the use cases. So everybody has the problem that this slide illustrates. This slide is automatically generated by MetaMask, and this is the package dependency relationship among the JavaScript packages that are used to build MetaMask. The purple dot in the lower right, that is the package that MetaMask themselves wrote, that is actual MetaMask application, and all of the rest of this is third-party code that is linked in. This is not unusual. NPM reports that a typical JavaScript application, about 3% is new code written specific to the application, and 97% is third-party code that's linked in. And for JavaScript, as it is without SES, for, so to speak, normal JavaScript, everything is completely vulnerable to everything else. Every single module that's linked in here has complete ability to corrupt everything else going on within that same application. And that's an intolerable degree of vulnerability. And what we've seen, we've actually seen attacks where there's an innocent looking malicious upgrade to a package deployed on NPM, where the upgrade is targeting some specific victim. In this case, one called the event stream incident, where a event streaming library was upgraded in order to attack a Bitcoin wallet and steal the keys in order to steal the money. And in JavaScript, this is completely open. There's no realistic ability to even resist that form of attack. What's going on over here is this is the graph visualized with regard to the concerns that MetaMask has, given that all of this code is running under SES. So now I can explain the colors. The colors, the different dots are colored according to how much authority is given to the different modules, how much access the different modules have that enable it to do damage to the world outside of itself. And the ones that are labeled green have been given no dangerous access directly. The ones labeled orange have been given some dangerous access, and the ones labeled red have been given a tremendous amount of dangerous access, enough that if the red is malicious, you're still in a lot of trouble. So what the result of operating in this way is that the burden of reviewing the third-party code has narrowed tremendously. And you start with the red dots, and this is, again, the MetaMask interface to this, where you mouse over the red dot, and it shows you what it has access to. And in the absence of SES, in normal JavaScript, you basically have the same graph with all of these dots colored red. You have no idea, you have no ability to focus your review efforts. Anything might clobber everything. So, how did we do this? When we started, in 2007, when I got on the committee in 2007, the current JavaScript was ECMAScript 3. And ECMAScript 3 was a tremendously messy language with various aspects that gave kind of non-local scoping, that gave non-local causality traces. It was just a complete mess with regard to trying to get any control of what happens during computation. So the first thing we did when we defined ECMAScript 5 is ECMAScript 5 added a strict mode, which you can think of as mostly a subset of ECMAScript as a whole. And the important thing about strict mode isn't that it added anything, it's what it took away. It was a subtractive step. It left behind the worst mistakes of JavaScript, which are the ones that are in that red band. However, ECMAScript strict still has misfeatures that prevent defensive programming, that still don't make it possible to narrow your effort to review for vulnerabilities. In particular, all of the primordials, or the intrinsic objects, the objects that exist before code starts running, like object and array.prototype, all of those objects are completely mutable in normal ECMAScript, including strict mode. And everything shares one global object, and the host's authority, the authority to affect the world outside the host, the file system or the document or the network, is by virtue of objects put on the global. So that means that it's ambient authority. It's authority that is simply implicitly in scope to all code. So again, any piece of code can damage everything without limit. So we engaged in our methodology again, and SES is mostly defined in terms of what it leaves out. So it leaves out the mutability of primordials, meaning that the primordials, all of these objects that exist ahead of time, are completely pure, are completely immutable, contain no ability to cause I/O. And the result is that sharing those objects, which everything in an application implicitly does, is harmless. The other thing is that the global object was the main thing that caused the ambient authority problem. So we introduced this new abstraction called the compartment, which this talk is all about, that enables you to create separate protection domains on a per module basis. And have them evaluate, execute in different compartments that have, where each compartment has a different global scope. And the important thing is that after all of these subtractive steps, we have removed very, very little of the JavaScript language standard. The vast majority of the JavaScript language is unchanged, and much old code, much existing JavaScript code that was written unaware of SES still works just fine under SES. Google verified that in the Google Kaha project. Salesforce has verified it, supporting a 5 million developer ecosystem. Gorix verified that. There's a lot of experience now. Node has done some large-scale experiments. There's a lot of experience now that says that a lot of old code works fine. But of course, the old code written without knowledge of SES can't make use of SES to express security policy, to control the authority given to other code. So the fact that that old code runs under SES means that new code that is aware of SES can express security policy for controlling the old code, as well as controlling other new code. And the new code expresses that policy primarily by use of the compartment API. TC53 brought us yet another perspective about drawing these subsetting relationships, which is when you're doing software for an embedded device, a lot of the things you want in the language during development time are not things that you need in the shipping chip that goes out with the device. You generally try to remove things that are only useful during development and only ship what's needed to run in the shipping product. So the primary one is the ability to evaluate JavaScript strings. The typical embedded device, all of the source code only exists up front during development time. And once a chip is made to ship in a device, it's typically the case that that new source code, the device itself does not need to be able to accept new strings of source code and parse and compile and run them. So you save a lot of memory by simply omitting evaluators from what I'm calling the typical TC53 configuration. So SES still includes the evaluators. It's important for the other like web uses, blockchain uses, server uses of SES. But in order to serve the typical TC53 use, we need to think through the ability to create a meaningful SES configuration that omitted the evaluators. And that same issue reflects how module source code is handled. SES as a whole, like JavaScript, has to be able to accept has to be able to, at runtime, go out and obtain new module source code and parse it and compile it and turn it into a module that it links together with other modules. In a typical TC53 configuration, all of your module source code, again, exists all at build time. It all gets pre-compiled into the static information that's derived by pre-compiling the module. And then the static information, in order to express security policy, in order to create these protection domains, all of the dynamic linking, instantiation, initialization, and wiring of these modules together by imports, that all does need to happen at runtime on the shipping product. So that's sort of the residual functionality that needs to be on the shipping product. And it was very clarifying for us to structure those additional elements I've put on the slide such that the part that's in the TC53 configuration can be fully functional in a configuration where the other abilities have been omitted. Full JavaScript has a notion of distinct realms. In the browser, where it's most familiar, every time you create a new frame, you get a brand new JavaScript environment, and these environments can interact with each other. There's a realms proposal that we've been collaborating with for creating these things, but and SES does assume the realm API for the overall SES use cases, but again, for the device, there's really no reason for realms. Realms are very memory expensive, and they're a coarse-grain, heavy isolation mechanism. And if you only have one realm, one set of globals that you've frozen that are already configured for SES safety, then the compartment gives you all of the security benefits of an isolation mechanism at a tremendously lower cost, as we say. Some of the omissions also reflect omissions that we see outside of devices for other reasons, like CSP is content security policy, which is a configuration for turning off runtime evaluation to try to suppress script injection. So people have already on the web done engineering around living without the runtime evaluators. And separately, many applications are bundled together during development time, bundled together into one big file, which is shipped all at once, and then no further code does get loaded, even if the underlying system is able to. So engineering to live with a bundler where the entire bundle gets loaded at the beginning of the world, again, has a lot of overlap, is aligned with the engineering we're doing that serves the typical TC53 purpose. And the reason I say typical, by the way, is I want us to remember that there will be embedded configurations that do want to accept code at runtime, and that will be and will therefore exceed the green box here and include some of the elements in the yellow box. But it's important that the typical one continue to be very lightweight and with very, very good security properties.
So Mark, one comment or question?
Yeah.
You talked about the content security policy, CSP, for eval and function, and then also bundlers for dynamic offloading. Those are both out of band mechanisms from the language, right?
That's right. Oh, actually, not quite. The language provides the host hook,
right, that
enables the host to turn off the evaluators, and that is actually why Moddable is able to ship a system in which eval and function do not work in the device while still being conformant with JavaScript, is because the JavaScript standard enables the host to suppress them.
Right, but there's nothing in the language in any standard version of the deployment language that lets you do that, similar to bundlers. And so, to your point exactly, that the restrictions you're talking about in sort of the typical TC53 that exclude those same things are also out of band mechanisms. So there's precedent for how those are being handled.
Yes.
Not just the functionality they offer.
So actually, I'm going to say yes and no,
okay, because
one of the things that we're proposing here, which may fall inside or outside the typical TC53, that remains to be figured out. But for each of these host hooks, what we're proposing is to actually reify the host hooks so that JavaScript code can act as host to other JavaScript. Right? So the overall SES, the compartment API in the context of full SES would bring out into these host hooks everything that JavaScript normally delegates to the actual host, so that no matter what host you're running on, you can emulate any other host. And we'll be talking about that in a few slides coming up. Okay. So the methodology that we've been engaged in of omitting things in order to get a more disciplined language, a more well-behaved language to better support security is also, of course, aligned with the minimization of memory and the omission of evaluation in the TC53 case was driven by the need to minimize memory. But security and minimizing memory are again aligned because both of them benefit from simplification. So in order to understand the difference between normal JavaScript and SES, we need to understand what this initial heap of intrinsic objects look like, how they're connected together. So here's a representative sample of some of the more important objects. The thick bidirectional lines are a constructor and the constructor's dot prototype pointing at each other, pointing to the right with the dot prototype property, pointing to the left with the dot constructor property. The upward pointers are inherits from. So function inherits from function.prototype, function.prototype inherits from object.prototype. Some of these objects are what are called undeniables or undeniable intrinsics, which is they can be reached by syntax. So no amount of surgery on the primordials can deny code access to those objects. And there's the normal JavaScript global object that has global properties, property names for the entry points into this graph. So those are the properties pointing at those entry points on the global object. And the global object now also has a standard name for itself, which is global this. Now, there's a special relationship between some of these objects and the global object, which is the function constructor and the eval function both evaluate code with the global object as the global scope. When code being evaluated uses a name as a global variable name. That global variable name is aliased to a property of the global object, so that anything that's a property of the global object can be accessed in that manner. Other than those two, other than that relationship, nothing else in this heap points back at the global. If evaluation is turned off, for example, there's no way from the rest of the heap to navigate back to the global. And then the global is where host objects appear. Host objects are the additional objects that are not part of JavaScript, that are specific to a given host, that are placed on the global in order to give JavaScript code in that context the ability to ask the host to cause effects on the outside world. In this case, in the browser, the document object that gives the JavaScript code the ability to talk to the user. So this ability to talk to the outside world, the ability to cause effects on the outside world, to engage in I/O, is exactly what you need to not grant by default in order to be able to get control over what powers code has. Any code that has the power of being able to get to the genuine document object can corrupt the entirety of the application's interaction with the user, which is pretty bad. We also color date, which is part of the language, red because it has a fairly innocuous power, but it's still a genuine power, which is the ability to find out, to report at the current time. And that's a form of, that's access to an input event. So for both input and output, for any direct access to I/O, we consider that to be a special dangerous category. Because the global object refers to those dangerous objects, it's dangerous. And because the eval function and the function constructor evaluate code in the context of that global object, that's dangerous. So what we do to turn regular JavaScript into SES is we just separate the heap conceptually into these two portions. There's the shared intrinsics, which we make completely harmless, completely transitively immutable, free of I/O. So date is still present. It can represent date objects for rendering dates and parsing dates and all of that, doing date arithmetic. But It cannot read the current time. The function constructor that remains in the frozen intrinsics, the slash through it, relates to the CSP thing we were just talking about. That one has been disabled. It cannot evaluate code. And what's pulled off into the start compartment is a global object, pointers like object into the shared intrinsics, its own set of evaluators which are specific to this start compartment, and the initial authority that comes from the host. The host still needs to provide initial authority to the application. So for example, in a browser, it might still provide a document object in the start compartment. But in this case, we can say very strictly that there really are no back pointers from the frozen shared intrinsics back to the start compartment. The start compartment is in no way special, and therefore code running in that start compartment can start a new compartment where the new compartment has its own global, its own evaluators, and otherwise points into the shared intrinsics in the same way, but doesn't have anything dangerous on it. So this start compartment can be completely isolated, and you can create multiple of these things, and they're completely isolated from each other. But the start compartment code, the starting code, can also grant it virtual host objects. So for example, it might give it a global for a light bulb device. Even if it's running on a browser, it could still use this architecture to pretend to the code that it is an embedded host providing the light bulb, and then the code running in this compartment might think it's running in a start compartment. It can't tell. It's running in an emulated start compartment, and it sees light bulb. So this enables JavaScript code to act as hosts to other JavaScript code. This is a form of virtualizability. And it's incredibly lightweight, as we'll see.
Sorry, could I ask a question?
Yes, please.
And the function constructor there is crossed out. What is the relationship between that and the one that isn't crossed out?
Good. I'm glad you asked. So normally, there's this bilateral pointing relationship where the function constructor has a dot prototype property pointing off to the right to its prototype. And the prototype has I said that wrong. The function constructor has a dot prototype property that points at its prototype. And the prototype has a dot constructor property that points back at its constructor function. Over here, the bidirectional pointing, the bidirectional arrow is between the function prototype and the disabled function constructor. So this disabled function constructor, again, is conformant with the language because the language enables a host to disable a function constructor. And the result is that anybody navigating by following properties cannot, starting from a frozen intrinsic, by navigation, come to a working function constructor. There's no back pointers. But the function constructor that is off in each compartment, the per compartment function constructor that works, that evaluates code in that compartment, its dot prototype property still points at the shared function prototype. And any function that function constructor makes is a function that still inherits from the same shared function prototype. And one of the things that's really cool about that is that a function made by any compartment, if that function is passed to code in any other compartment, and the code in the other compartment says instance of function, the answer is yes, because the JavaScript instance of algorithm goes from the constructor to the prototype by following the prototype link, goes from the object up the inheritance chain and sees if they meet at a common prototype. And therefore, preserving the dot prototype property preserves instance of. so that you don't have a anomaly of code in one compartment interacting with code in another compartment. Instance of just works.
That's great.
And the result is that you can use this at fine grain. You can take multiple modules that were, and this goes back to what I was showing with the MetaMask and the graph of packages depending on each other. That means different packages can be evaluated in different compartments, even though they're written under the assumption that they're running in just normal JavaScript code. And quite often they can be just evaluated in different compartments, different powers, and still linked to each other in such a way that the linkage works, but they're each given different authority because they're evaluated in different compartments.
That's correct.
Okay. And the compartment object itself, which is each of these outer boxes, the green box that you're seeing on top, that's an instance of this new abstraction compartment. So we also have to account for the abstraction itself. So we have compartment follow the same pattern that we saw with the function constructor, where there's a compartment constructor per compartment, but they all point at the same shared compartment.prototype, and the compartments.prototypes.constructor property points at a disabled compartment constructor. The compartment constructor itself is not an evaluator, but by making the constructor per compartment, we enable a relative name mapping property that we'll see shortly for the import namespace. Which finally brings us to the actual compartment API. So I'm actually very, very happy that all of this work for so long has resulted in an API that is this small and that is as tremendously expressive as we're about to see. And this piece of code deals with 3 separate concerns. It deals with the global variable namespace, being able to give different code, different namespaces of global variables. It deals with the module import namespace. So when a code in one compartment says import foo, it can be given a different foo than code in another compartment is given when it says import foo. And host hooks, which is the thing that Peter and I were just talking about, which is JavaScript delegates various pieces of behavior to the host. And for the various things that JavaScript delegates to the host, we want to be able to have JavaScript code instead provide those behaviors to other JavaScript code so that JavaScript code can emulate a host to other JavaScript code. And that's the controlling versus controlled code. The controlling code creates a new compartment for controlled code, and in creating it provides the host hooks such that the controlling code is acting like host to the controlled code. So we start with global variables. This is the part of the API that deals with global variables. When you create a new compartment, you say it, you do it by saying new compartment. That invokes the compartment constructor with a set of arguments, and the one relevant to the global object is this first argument called endowments. And that's just an object for providing extra properties like bulb. So when the start compartment might created that new compartment, endowing it with the emulated light bulb, it could have done it, typically would have done it by simply including an endowments object that has an own property named bulb that has an object created in the start compartment's code, which is the emulated light bulb. So you just put it there and those become extra globals. They become virtual host objects, as seen by the compartment being constructed. From a compartment instance, you can directly get the global object, so that if you're trying to control the compartment from the outside, you don't have to go through weird machinations to obtain the global object. And then if evaluators are not fully disabled, if the evaluators that are per compartment are enabled, which they won't be in a typical TC53 configuration, but we're trying to explain also how this fits into the larger language, is that you also have an evaluate method on the compartment instance, which is much like the eval function within the compartment. But what's the purpose? Why is it that controlling the global scope is so powerful? And the way I'd like to explain this is by making another hardware analogy. On the left, we see a relationship we're very used to in conventional hardware, where an instruction set is divided between user mode instructions and system mode instructions, where the user mode instructions are purely computational. They can't engage in any I/O. They can do data arithmetic, but they can't find out what the current data is. And so they cannot interact with any devices. And then there are system mode instructions, where code running in system mode, able to execute system mode instructions, can reach those devices. And there's a trapping mechanism such that code running in user mode, when it does something that exceeds user mode, causes a trap, and by that trap enables the system mode code to wake up and handle the trap. On the right, we see the analog with JavaScript, which is really miraculous how close this analog is. It's very rare for a programming language to have this pure separation between the language, which is almost completely free of I/O, and the host providing objects that provide all of the I/O. JavaScript has that separation almost perfectly, and that's what enabled SES to be such a pleasant transition, and why SES can run so much existing JavaScript code. So the analogy is that the JavaScript language is like the user mode instructions. The host's internal mechanisms, including the devices, are the host internals itself. And the JavaScript language provides the standard means by which JavaScript code gets the abilities from the host, which is to look up a global object like document. So the global object is the means that are provided for. And on top of this architecture, on the left, we build operating systems. We write an operating system kernel that runs that's written to use the system mode instructions. The operating system kernel, each operating system, the operating systems running on the same hardware can differ from each other. Each operating system has its own system call interface that's a designed API for making requests of that operating system. And the different processes, the operating system also separates processes from each other. The different processes, by using that system call API, are able to ask the kernel to cause effects on devices. Similarly, in normal JavaScript, there's code, the code running in a realm is just global code running in an execution context, but it only obtains the ability to cause effects by looking up host objects in the global scope, and then the APIs of those objects are the APIs designed that are specific to that host, like the browser host APIs, And when JavaScript code invokes a host API, it's effectively doing a system call. And by doing that system call, it can reach the external devices of that host, like in the case of browser, the user and the network. And this has obvious analog in the TC53 embedded case, where it's all about controlling devices like light bulbs. Yeah.
Question. So here you're saying that you can access I/O only through host objects. How does that how do I say this? Because you can also access I/O through imports, where the import may be a native module. And obviously the import itself, like if you're importing the FS module, you import it through a require function, which is actually injected as a parameter.
I'm sorry, you import it through a what function?
The require function.
Oh, require,
is a parameter
right.
To the
So require is not defined by JavaScript.
Yeah.
It's defined by Node, and require itself is a host object.
It is a host object, but it's not accessible through the global objects.
That's true. Node injects the require object on a per module basis, which is still in the scope outside of the code. But you're right, it's not on the global. And it's outside what the language directly provides for, which is interesting. So 2 points. With regard to the points that we'll be making, since we're going to move towards compartments, the ability to have different require functions exposed to different pieces of code would actually fit better with the compartment API.
Okay.
But in the typical TC53 context, we're actually not going to, my understanding is we're not going to try to support require. We're going to try to support import and module, and only do things with modules, but your point is still also valid for modules. This thing about the global object, that was true historically, but now that modules are in the language, modules themselves that are importable can be the means of reaching devices. And we'll be dealing with that coming up, but the host object is sort of the right conceptual place to start, and is historically where hosts have provided powers. So on the left, we see one of the things a operating kernel can be designed to do, which is to set up its trapping mechanism so that one process, the process on the top, can create the process on the bottom in a way that the process on the top controls, such that whenever the process on the bottom traps, the operating system, by prearrangement, reflects the trap back up to the process on the top. And the result is that the process on the top is able to act as a virtual operating system for the process on the bottom. And this is how cleanly virtualizable systems, going back to the IBM 360 and OS 360, enabled easy virtualization of one machine and operating system on another. In the case of SES, all of the objects that are global to the realm, the shared intrinsics, they're all frozen, so they're not a communications channel. They're not a means for things to affect each other. And that means that the compartments are now the separate units of isolation. And through the compartment API, we're going to allow one compartment, the one on the top, to instantiate the other compartment such that whenever the other compartment reaches for a global, the global that it gets is the one that's according to the compartment on the top. And the result of this trick is the process on the bottom is seeing the illusion created for it by the process on the top. It might be thinking it's running on a completely different host with different devices that it thinks it's controlling, all of which is just emulated by the process on the top. And likewise, compartment to compartment on the right. So I saw a talk of Peter's showing SES running on a light bulb. And what he first showed was an application, an app running in the start compartment that simply talks to the host to control the light bulb. And then showed another configuration where the app is not given direct access to the light bulb. Rather, another compartment is created first, which is a light bulb attenuator that creates a virtual light bulb that out of the physical light bulb. That the physical light bulb might blink so fast that it causes seizures. And the app sometimes, let's say, accidentally or on purpose does that, or the app, or more interestingly, the app has a vulnerability such that a third party can corrupt it. So that it would do that, or whatever, for whatever reason, the app is using the light bulb in a fully featured way, and we'd like to restrict it. So we can impose this attenuator that creates a virtual light bulb and passes through a subset of the requests or some limitation on the request to the actual light bulb. And the result is that the same app that was running in the first configuration is now running in the second configuration, thinking it has direct access to the light bulb. It's actually exactly the same code. It's not aware that it's running in an emulated environment. And I want to verify this with Peter and Patrick. What I remember from the talk is that this entire picture with all the virtualization going on is running in the light bulb in a machine that had 4K of RAM and 1 meg of ROM. Is that correct?
ROM is correct. The RAM is more like...
I'm sorry, 40K.
40 is right, yeah.
40K. I actually...
What it was using was less than that, but 40 is a good...
Okay. Okay, I actually meant to write down 40K, yes. Okay, good, 40K of RAM. So that's amazing that this level of virtualization that's analogous to machines hosting other virtual machines and virtualizing operating systems done at the language level with objects being the protection mechanism can be done practically and securely on a machine with 40K of RAM and 1 meg of ROM. So that dealt with global variables. Next on our plate is module imports. And module imports is where we've actually spent most of the design over the last 6 months in the SES group, is figuring out how to integrate modules into SES that meets all of the constraints, including this separation of what's available in build time versus what's available at runtime. So this is the elements of the compartment API that's relevant to that, which I will explain after a brief intermission. Does anybody have anything that that they'd like to discuss at this point?
I have some questions, but I think they'll be better served at the end after you've covered the
Okay.
modules.
Okay, I'm still going to take a breath.
If you moved your car at the start of lunch
Yes.
and you're in a 2-hour spot, now's the time.
Now is definitely the time. But you should move to the 3-hour lot right there because it goes to 5 and then you don't have to move your car.
Unless you were previously parked in the line.
Yes, if you were already parked in that lot or any of the Lime Zone street spaces, don't park in that garage.
If
So
you moved
are
your
we-
car into lunch, you get another.
Security was complicated. How all parking was
Yeah. We do have maps available actually on our brochures.
So does anybody need to move their car? Okay.
Yeah.
Okay, I go on. So this is the part of the constructor API that deals with control of the import namespace. The part of it is this other argument to the constructor, which is called a module map, that maps from names of modules as might be mentioned in an import statement in the code being controlled, which let's call it the child compartment, mapping that into a name of the parent compartment. So right now I'm only going to talk about the name to name mapping, and I'm going to leave aside the name to module space mapping. But the general form of this is it maps from name either to name, recognized because it's a string, or to a module namespace object, whose significance I'll describe later. And there's to get code running in the compartment, you have to start the code somehow. So there's a import now and an asynchronous import, both of which conceptually do the same thing, just they differ in terms of when it happens. I'm only going to talk about the synchronous form, import now, that you give it a module name. It needs to be a module name that's in the import namespace of that compartment, and it actually initializes, instantiates and initializes that module, which involves also creating the full instantiated, initialized, and linked together graph for everything that it synchronously imports. And then returns what's called the module namespace object as a result. And that's the object whose properties are all of the exports from the module. That's an existing JavaScript concept and is represented in JavaScript right now with the import expression, which is asynchronous and corresponds to the second form here. That simply returns a promise for a module namespace, such that at some later time, it becomes the actual module namespace. In the embedded configuration, the synchronous form is much more relevant than the asynchronous form. So to understand this, I'm going to make yet another hardware analogy. And I need a glass of water. So operating systems in enabling one process to control another process doesn't just do it through a trapping mechanism. The MMU mapping virtual addresses to physical addresses, when there's a physical page when the page is already a physical page of RAM, it doesn't trap through the MMU. The MMU just translates address to address, and the memory lookup proceeds at full speed. And then it's only for the addresses that don't correspond to pages that are currently loaded. Only for them does a trap happen, such that the result of the trap is hopefully that eventually there is a page of physical memory that corresponds to that address, at which point the mapping can proceed and computation can proceed. So the analogy that I'm making with this picture is that the child specifier is just the spec term for a module name as might be mentioned in an import statement. And I'm purposely skipping some details here that will become clearer much later in the talk. But the specifier is the name of a module in an import statement that's running in the context of the child compartment. The module map that the parent provided that provides a name-to-name mapping is mapping names that the child sees into names that the parent sees. And when that corresponds to a statically loaded module, which is the only case that will happen in the typical embedded case, there won't be any traps because of missing code, because at runtime there won't be any code missing. So in that case, there's just this mapping from name to name followed by the lookup of the module, and then the module gets instantiated again in the child under the new name. And we want to do this multiple levels deep. So if the child creates a grandchild, the child can provide yet another module map, and we follow the object capability rule, which is the intuitive rule, that the child can only give to the grandchild what the child has, and the child has only the subset of what the parent had that the parent decided to grant. So to explain the actual semantics of all of this module mechanism, I'm going to do it in terms of the state that is in the ECMAScript spec, the various state variables. But I'm not going to do it as organized by the current ECMAScript spec, because the current organization of those state variables into different record types in order to explain the semantics. These are purely internal record types. They're just explanatory. They're not exposed in the API. So we can refactor this to move things around into a different internal explanation without affecting the semantics at all. And this sets us up to explain better the semantics that we want. The other thing is, and this is what I want feedback from Peter and Patrick, is that the new factoring, I believe, also explains what implementations actually do much better than the old factoring. So in the new factoring, there are 3 separate record types, none of which inherit from the other, but they do point at each other. The blue fields, which were scattered among abstractions on the left, I've gathered those together into the static module record, and that is all of the information that is gotten by compiling a module, by parsing it, by doing the scope analysis and all that, but doing it for module source code in isolation without doing any cross-module analysis. So that's the module static record, and that would be the thing that you put in ROM that results from having that source code analyzed at build time. Then there's the module instance, where you can have multiple instances of the same static record. And that's like you have multiple closures or function objects per function expression source code, or multiple instances of a class, same kind of relationship. For a given module static record, you can have multiple instances. And so the green fields are the ways in which one instance can differ from another. And then the module instantiation, which are the red fields, I've gathered those together into this separate module instantiation thing that points at the module whose purpose, module initialization, those fields are only relevant during the process in which a module graph is being instantiated, linked together, and initialized. And once you have a fully initialized graph of modules, none of that red information is relevant anymore, so you can drop it. And that means when you're reasoning about a instantiated set of modules, you can simply not reason about the red fields. You can narrow your view when you're reasoning to only the green fields and the blue fields. So Patrick, does the right-hand organization correspond more closely to the way you actually implement it?
Yes, much more.
Thank you. Thank you. That's very, very satisfying to know.
Yes.
Okay. And JavaScript has two kinds of code that evaluate. So the column on the left explains how modules evaluate, how modules execute. And the abstraction on the right is just a renaming of the existing JavaScript abstraction, which for parallelism calling the script instance. But this explains how non-module code evaluates. And the important thing is that the analogy between these two things to explain evaluation is quite strong, so that all of the mechanisms that help us explain and refactor evaluation on the left, the result applies equally to controlling the execution of scripts. And of these two instance objects, all of the important action is happening in this thing called a realm record that they both point at, which has this state over here. So that's the remaining state that's necessary to explain execution, to give semantics to execution. And so far, only a pure refactoring. This is just changing how you explain the semantics, didn't change the semantics. And the state variables are just the same state variables. I didn't change a single state variable. I just rearranged where they were. But now that we've done that, we can explain what we want. So we're going to take this explanatory abstraction of the realm record and turn it into the reified abstraction of the compartment. So a compartment instance is now an object exposed to JavaScript created by the implementation that has these internal fields. The internal fields, the double square bracket, that means these are not properties exposed to JavaScript code. These are internal things that the built-in methods of compartment can operate on. So it's how you explain the behavior of the built-in methods. But then other JavaScript code can only invoke those built-in methods to cause these effects. These are the fields here are the same fields shown in realm record, but I added two more. I added the module map, which is the thing that enables us to have a per compartment import namespace. So the global object and the global global environment, is the thing that gives us a per compartment global namespace. The module map gives us a per compartment import namespace, and then the hooks field gives us per compartment host hooks. So the host behavior that's seen from within one compartment can differ from the host behavior that's seen from within another compartment. So now that we've got the internal state of the actual compartment object, let's now see how it corresponds to our API. Those elements of the API in bold on the right are about the bold-faced internal variables on the left. The global env, global environment, is the means by which global variable references become alias to properties on the global object. And the global object is the value of the global this. The endowments gets copied onto the global on initialization, and evaluation runs in the scope of that. The bold-faced elements in the API are about the module map, and that corresponds, of course, to the module map element, which we'll be coming back to. And the options object, we add to both the evaluate and the compartment constructor an options bag. We did it to the evaluate sort of as a just in case there's options there we want per evaluation. We currently don't have any, but you can't add an options bag to the existing evaluators. So this seemed like a good opportunity to reserve space for that. But the important one is the options bag on the compartment constructor, because it's options in that options bag that is how the creating code, the controlling code, provides the host hooks to the controlled code. So let's take a look at these host hooks in the options bag. So that's those elements of the API. And now what I'm about to explain has much less interest to TC53, but it's important for explaining how SES as a whole fits into JavaScript, which is the ability to load code at runtime remains important for some embedded uses, in fact, but also necessary for integrating SES into the larger JavaScript world. Oh, I see. So we call these import hooks, once again in a synchronous and asynchronous flavor. And this corresponds to host hooks that are in the spec under different names. And the referrer here is gives us the ability to process relative specifiers. So when code within a directory says import .. /foo, and it's climbing out of the directory, you need some way to handle sort of the algebra of the slash language. But you don't want to build that into the engine. It's not built into the spec. So this is a general hook that gives you the ability to handle that, and the same hook gives the ability to load code dynamically. And this, in order to be in a configuration in which this option is accessible, we do have to reify the concept of the module static record as well. So the reified form of the module static record is actually still quite a simple thing. but now it does become a reified concept available in the language, and this hook is required to provide one. So, so that options bag corresponds to the hooks field at the bottom. And it's the overall module picture is useful to take a look at both the module map and the import hook. So the hooks field at the bottom has more than just import hooks, but I'm only showing the import hook. The module map, what I've explained is the mapping from name to static module record, where the static module record gets separately instantiated inside each module that addresses it. I realized that explaining the next step, the module instance, is, I think, best put aside to a later talk, unless Patrick wants to explain it, which would be wonderful. But I decided that at this point, having explained this much and pointed at the part that remains to be explained, I will now take questions, and I can turn off recording first if you prefer. You don't mind? I'll take this question on the record.
The previous slide, I may have missed some, or I'm just not sure, but what is the refer in the import now hook?
Okay. The refer is the name of the module doing the importing. So if, let's say that you have a module foo that's nested inside a subdirectory. And then the module foo says import ... /bar. So now, in order to know how to interpret the ... /bar, you have to know that it was foo importing it, because you have to know where in the directory it is. If it was something that was higher up in the directory tree and it said the same name, you would interpret ... /foo differently.
Okay.
So the specifier is the name of the importing module, and then the specifier, sorry, the refer, did I say that wrong? The refer is the name of the importing module, and the specifier is the name that it utters in the import statement of what it wants. And it's the responsibility of that hook to understand how the name of the importing module and the name that it's requesting relate to each other, so it can do things like follow the slash algebra. But it's not just trying to map that to a new name. As a hook, it's responsible for actually producing the module static record.
That makes sense.
So I'm gonna, so the module static.
Should I turn off recording?
Oh, no, you're,
Okay.
thank you. The static module record is something new that doesn't exist in if it's just to resolve the module algebra and you do things like that. If it were, it probably isn't. But if it were, wouldn't it be enough to just return like a new module specifier? Like just
Yes.
a string?
Yes. So this is the latest and freshest invention, and therefore the least refined part of it. But in a situation where you don't need, for any other reason, to reify the module static record, in particular, there's no dynamic loading. If there's no dynamic loading, then something that goes from specifier and refer to specifier would be perfectly adequate. And in fact, we went through that as a step towards getting here. So you could do the same kind of thing we're doing up here, or the same kind of thing we're doing over here, which is you could say this is mapping to a name or a static record. I don't know that that's a good idea. Like I said, it's the latest invention, so still the part that's least well formed.
So this could, if it's new and it's very new to me, so we just say it like, so this potentially circumvents the module. because it could load from anywhere and return the static module.
That is correct, but it can only load from somewhere it can get to.
Sure.
But yes, if it can create a module static, that's the intention. Is if you're trying to create, let's say, a virtual browser, what the host, the host that's emulating the browser, the code that thinks it's running in a browser, the code that's running in a browser can say, I want the thing at this URL, and a fully faithful browser emulator has to be able to dynamically go out onto the web, engage in I/O, find the source code, parse it, turn it into a static module record, and provide it. So the things that its parent had to provide for it is it had to provide it. There's basically two crucial capabilities that it needs in order to do this. It needs the ability to find the actual module source code wherever it is, and it might be that and it could just be that the kind of host it's trying to emulate is such that it just calculates new strings out of its own imagination, in which case it doesn't need a capability to do I/O. And then the other one is, from a capability theory point of view, really not a separate capability, but it's something that you can separately control the availability of, which is a primitive for turning module source code into a static module record. And if you don't have, so that's basically, that's sort of, you can think of that as yet another evaluator. So the evaluators are the things that go from source code to something that can execute. And this would also go from source code to something that can execute. But the means by which it executes are now a little bit more direct, more indirect than for the other evaluators.
You can think of the import hook as a really obscure way of calling it out.
It's interesting. I'm just sort of trying to look for it.
The important API of the module, the static module record could be the important API that it provides, such that it's necessarily not fully opaque in order to accommodate the uses it needs to accommodate, is the API tells you what are the names it imports and what are the names it exports, so that you can write an algorithm that's processing only static module records that follows the import names to figure out what other code to load to create other static module records, so that it can create the entire synchronous dependency tree of static module records. In order to do that, it has to know what the names are that it needs to be able to satisfy. Now, it's not doing any linking, but the knowledge of the names tells it what kind of linking will then be expected when these things are instantiated.
Are the other hooks optional when provided as in the compartment constructor?
Yes.
And if they're optional, what is the behavior inside module if they're not provided?
Okay. The behavior is that the hook environment that the controlling code is in is implicitly just granted forward to the controlled code. And if you wanted to suppress that, you can just as easily provide an empty object. And if you provide an empty object, then you're suppressing all the hooks, rather than which kind of leaves you in some cases with a broken JavaScript, because some behaviors of the host are expected.
If I can ask a slightly different question. So there's three different ways essentially to grant power to a module. If I understand correctly, there's the endowments through the global objects, there's the module imports, and then there's just passing information or objects with capabilities as parameters to function calls
That's right. That's right. So this is all of this design is about the initial authorities that a module gets. Once a module's been instantiated, now you just have live objects. Now you've got a live capability system. And for new code, what we want to do for new code, and what we've been practicing at Agoric, is that we do very, very little wiring of initial authorities. We try to have most things that are created have their initial state actually be immutable, what we've been calling pure, and then do a lot of our wiring among instances through genuine parameter passing. The reason why this is all needed is that with this, we still get to run a tremendous amount of existing JavaScript code. If we did not have the ability to provide authority for initialized time in a way that we can isolate and separate and multiply instantiate, if we didn't have that ability, if we could only run pure, execute pure modules, then there would be essentially no pre-existing JavaScript code that we could run.
Okay, so would you recommend then for TC53 in developing these new APIs for sensors and I/O and that to try and do that parameter passing as a way of providing power to a module more than say using a global object or imports to provide power?
Okay.
Is that what you recommend?
So that's what I would recommend, but I'm not an embedded guy. So let's just take that as a naive recommendation to then get feedback from all the rest of you at TC53 if there are embedded trade-offs that argue against that. For example, if it creates, for some reason, more memory pressure than doing it this way, which doesn't seem likely, but does seem possible. Okay, I think we're done, and I will stop recording.
Can you, so you gave a variation of this presentation at TC30.